All right, folks, let's get going. In this first video, we are just going to blast through everything here in Chapter 1, which is about straight lines. And I think if you're taking the HL course, you probably know your straight lines pretty well. But just in case, let's just cover the basics here. If a line crosses the x-axis, it's got an x-intercept. If a line crosses the y-axis, it's got a y-intercept. The gradient, also sometimes called the slope of a line, just tells us how steep it is and whether it's going up or whether it's going down, and this gradient can be calculated using this formula right here when we have 2 points. The first one we're going to label x1, y1. The second one we're going to label x2, y2. It doesn't matter which one's which. What's important is that 1 goes with 1 and 2 goes with 2. And then we just substitute the numerical values of those coordinates into our formula here, and we get a measure of the slope. Two lines are parallel if their slopes are equal, and two lines are going to be perpendicular if their slopes are negative reciprocals of one another. So algebraically, that means that we can satisfy the two equations written down below. So I will add here that a vertical line is going to have 2 points with the same x value. So that would mean that looking at our slope formula, we'd have a denominator of 0. So a vertical line has an undefined slope, whereas a horizontal line would have 2 points with the same y value. So that means that our numerator would be 0. So then a horizontal line has a slope of 0. How do we write the equation of a line? We got 3 different ways to do it. The first one on this page, and it's the most important one as far as I'm concerned, is called point gradient, also called point slope. I'm just going to use those two words interchangeably, by the way. You feel free to as well. However, IB exams, and certainly this textbook, are going to use the word gradient. They're not going to use the word slope. But I know my video is primarily directed at an audience learning in the United States of America, so we tend to use the word slope here. Anyway, moving on. So if we know what the slope is of the line, then we can write the equation of the line like this, where that's the y-coordinate of a particular point, that's the x-coordinate of the same particular point, and that's the slope as calculated with the slope formula from the previous page. Point slope is the best, especially once we get up to calculus, but really I think it's more helpful in most algebraic applications as well. However, we do have gradient intercept form, so that's just going to be written as y equals the gradient times x plus the y-intercept. So that's where the line crosses the y-axis, as we just saw. And then we also have general form, which there's a couple of shortcuts you can use with this. I've never particularly found a reason why I've wanted to use general form. The only reason that I mention it is that some IB questions will require you to write your answer in a specific form, and I've even seen a sample question for the new curriculum which required the answer to be given in this form. So yeah, it's possible that you're going to need to know it, so there it is. So let's just do one real quick. We want to find it in gradient intercept form, the line going through these 2 points. Let's just look at this really, really fast. So first we calculate the gradient using those 2 points right there. So we've got -1 minus 2, and then 5 minus 3. Simplify all that, we get -3 over 2. And then we know it goes through the point. Well, they've chosen the point A, but of course we could have used the point B as well. We're going to get the exact same thing. In fact, there's the work for that if we wanted to use point B instead of point A. And then we just do some algebra to transform from point slope form, which is correct. And if the problem had not said that right there, if it just said find the equation, I would have said this is a final answer, or this is a final answer. We don't need to do any extra work. In fact, it's a waste of time to do extra work, but whatever, we can get down to the slope-intercept form either way. Okay, slightly different look with these problems. Here we need to figure out some value. In the first one, we're figuring out m. In the second one, we're figuring out k. M is our slope in the first example. K is the y value of a particular point on the line in the second. But the trick is really going to be the same for both of these. This is all about substitution. So in the first case, we've got a point right here, -2, 3, and that's an x value and a y value. So we're going to substitute those in. here and here. And then we're just going to do a little bit of algebra to solve for our missing letter, which is M. And then we can do the exact same thing in the second one. We can put in a 3 here for X, and we can put the K in there instead of the letter Y. And same idea, we've solved it. Okay, that brings us to section B, which is about graphing straight lines. I don't have very much to add to this page, so for the most part, just pause it and read it through, make sure you get it. The only thing that I will throw in here is the book doesn't mention graphing the line when it's in point-slope form. But really the only difference between point-slope form and slope-intercept form is in slope-intercept form, the point is the intercept. So really, if we just change this first step right here to say use the known point and plot that, then the rest of the process is the same. Let's do 2 of these real fast. So the first one we've got in slope-intercept form. So we're going to graph that. Let's go this way. So the first step is we're going to plot this point. That's the y-intercept. And then we know the slope is -1/3, which means we're going to go down 1. We're then going to then go over to the right 3. And that's our next point. We could get out a straight edge if we wanted to and connect those 2 points with a straight line. When we're taking exams, we're going to need to remember our command terms. This particular question does say draw, which means that it should be drawn to scale on graph paper with a straight edge. For part B, we've got it in general form. So the shortcut is to set x and y to 0. When x is equal to 0, this term goes away, and then that tells us that y has to equal -3. When y is equal to 0, this term goes away, which tells us that x is equal to 6, and then that gives us the y-intercept and the x-intercept, and then we just connect them from there. If you don't like that trick of setting x and y equal to 0, then please just rearrange this equation into point slope or slope-intercept and just do it that way. It doesn't really matter. Okay, that brings us to section C, which is about perpendicular bisectors, a topic which is being given a new and enhanced focus in the current curriculum compared to the old one. So first, let me just get this out of the way. So we've got 2 points here, A and B, and point M is right in the middle of them. So point M bisects line segment AB. So we've got congruency marks here indicating that. Now if I were to label this point here C, and maybe this line continues, let's call this point right down here D, it is true to say that CD perpendicularly bisects AB. It is of course not true to say that AB perpendicularly bisects CD, because CD has not been bisected. Certainly AB is perpendicular to CD, but it's not the bisector. So please make sure that you get the order correct. Now the important part about perpendicular bisectors is, number 1, any point along that perpendicular bisector is equidistant from both of the original 2 points. So point C is the same distance from A as it is from B, and we can say the same thing about D. And that can be proven using geometry and just congruent triangles. And then also, the perpendicular bisector divides the plane into 2 regions. So that means that any point that I choose over here on the kind of leftish side of that bisector, this point is going to be closer to A than it is to B, whereas this point over here is going to be closer to B than it is to A. Now that looks obvious, I think, but that has some important applications. In particular, in the mathematics applications and interpretations HL course. They do some interesting applications over there called Voronoi diagrams, which have further applications in like computer science and a whole bunch of advanced like university level math. They're actually pretty cool and fun to play with, but we should still know at least that basic fact just in case it pops up. Okay, so for example, in our course, they might ask us to find the equation of the perpendicular bisector. So here's just a quick picture of what's going on. We've got point A and point B. They've got a midpoint, so AB is bisected. We got a line going through that midpoint, which is perpendicular to the original line. We want to figure out what is the equation of this line here. So if we're going to find the equation of the line, we need to know a point that's on that line. What point are we going to choose? Hopefully it's obvious. We're going to use the midpoint, and then we need to figure out its slope. And that'll be derived from the slope between A and B. So first of all, let's get that midpoint. The way to find that, the midpoint is always it's like the average point in between the other two. So what I mean by that is this right here. So we take this x value 4, this x value -2. We add them together, we divide by 2, we get 1. Take the y values, 7 plus -3, divide by 2, and you get 2. So the coordinates of the midpoint is 1, 2. Now we need to figure out the slope of the line. Well, we figure out the slope of AB, and that comes out to be -5/3. Since this line is going to be perpendicular to it, that means that its slope needs to be +3/5. Right? That's the negative reciprocal of -5/3. Putting that all together, okay, they've put it in to looks like general form here. I wouldn't have done that. I would have just said y -2 is equal to 3/5 times x minus 1. Point slope form, call it a day. It's correct, and it's the exact same thing as what we see there. And final section of the chapter is just about systems of two equations with two variables. Certainly you've seen this before. This is just the tip of the iceberg for us in this course. Later on, we're going to end up studying how to solve systems of 3 equations with 3 unknowns, and then I'm even going to push you into thinking about 4 and beyond, because that's something that you end up doing in university mathematics when you study linear algebra and stuff like that. So important topic here, and we've kind of got 3 basic ways of solving a system of 2 equations. One is going to be graphing, and that's we're not going to really do that with lines ever, but that is an important technique to use later on for more complicated functions. We'll see that in the following chapter. And then we've got substitution or elimination are going to be what we're going to do on paper. So if it's like paper 1, no calculator, those are the techniques we'll use. But then I'll also show you how to use the TI-Nspire to do this if it were a paper 2 question. So first of all, let's just do it by hand. So they want us to solve this one simultaneously. So I need to decide, am I going to use substitution or elimination? Well, since I already have the first equation has got y alone, I think it's the smart idea is going to be to use substitution and substitute in x minus 3 in for that y right there. And we see that's exactly what's happening, right? So we're taking the second equation right here. We've got 2x plus 3, but instead of writing y, we're writing x minus 3, and that's equal to 16. Now we have one equation with only one variable, so we do some basic algebra to solve for that, and we get x equals 5. Now we take that value, put it back into really either one of the 2 originals, and then we're going to get a corresponding y value, which is 2. Really, you'd want to check your work by putting x equals 5 into both of the original equations. You should get y equals 2 for each of them. If you don't get y equals 2 for both of them, then something's gone wrong along the way. If we wanted to see the picture of this, because it did say to illustrate your answer, there's the 2 lines. They've been graphed correctly, and they intersect at the point 5, 2. And that intersection is the key for what we're going to do later on with technology for solving more complicated systems of equations. But again, that's for another video on another day. Let's just look at one with elimination. So when we don't already have one of the variables alone, it's usually easier to use elimination, especially once we get into more than 2 equations. Then that's when elimination really starts to shine. So I definitely want to emphasize this technique as being an important one. So it would be really nice if, for example, this first one, if that had said 2x and 2x, then the technique you've probably seen is going to be to subtract one equation from the other. Of course, the coefficients here are not the same, so we're going to make them the same. This example is going to eliminate y, but of course we could eliminate x too, and I'll show you that in just a second. So we're taking the first equation and multiplying it by 3, and the second equation and multiplying it by 4. That way we've got plus 12y and negative 12y. And now if we add the two equations together, those are going to cancel out, and that's going to give us 17x on the left and 34 on the right. Dividing by 17, we get x equals 2. Putting that in, again, to both of the original equations, that's going to get us y equals negative 1. If I were to eliminate x, I would pretty quickly get y equals negative 1, and then just as easily figure out that x is equal to 2. Now let's look at the calculator. All right, so again, I'm not going to discuss the graphing method here today. That'll be for next chapter. Instead, let's just jump to the calculator. Our first step very, very often is going to be to press menu and then decide, well, what are we doing here? Are we doing statistics? No. Calculus? No. It feels like algebra. Oh, look at that. The very second option is solve system of linear equations. Cool, let me pick that. This is pretty convenient. There were two equations in the problem, so I tell it that. I could just tell it what the variables are. If the problem had, like p and q as the variables, I could type them in here, or I could just mentally substitute p for x and q for y or whatever. I don't care. Do it, whatever makes you happy. Anyway, then we just press OK, and then we just have to type the two equations into these boxes. So it's really easy. Let's just do the last one that we had. So that's 3x plus 4y. And so the x, all the letters are down here. X, y, and z are even in different colors, so you can spot them really easily. Then the equal sign is right over here next to the trig button. So that's equal to 2, and then we go down into the other box, and then we have 2x minus 3y, excuse me, is equal to 7. There we go, and then we just press enter, and it gives us the solution, which is pretty neat. So that's how to do it using technology. Final problem for this video, just to show you something a little bit more indirect that the IB might ask you. Here's a slightly longer problem. So we've got a system of equations, and we don't know precisely what the gradient is of that second line. All right, so let's answer this. Part A says find the gradient of each line. Okay, well, the second one has a gradient of m, whatever that is. The first one, we could rewrite this, and please do the work to check this, in the form y equals 3 over 2x minus 6. So that's our other gradient. Hence, big word in the IB. So hence means using this information right here. Hence, determine the value of m for which these equations do not have a unique solution. Let's talk about what unique solution means. When we have two lines graphed, what are the three options? Well, they could intersect at a particular point. That's a unique solution. They could be parallel. That has no solution. If there is no solution at all, then there is certainly no unique solution. And finally, they could be one line lying entirely over the other. So the two lines could be overlapping. In that case, there are infinitely many solutions. Every single point along the lines is a solution, but in that case, there is no unique solution because there's more than one. In this particular case, so we're figuring out the value for m for which the simultaneous equations don't have a unique solution. So first of all, what is that going to be? Well, in this case, it's going to be m equals 3/2. Because if m was equal to 3/2, check this out, this equation would be the exact same as that equation. And now it says explain what's happening. That means, like, which non-unique situation is it? Is it this one or is it this one? Well, since they're the exact same line, it's going to be the bottom one. So I would write down for part B, the two lines overlap. And then for part C, it says for any other value for m, of course there is a unique solution, find it. Well, we can work that out by setting the two equations equal to each other using substitution, right? The 6's are going to drop out. Here's what we're not going to do. We're not going to just divide by x to cancel those out. If we do, we're just going to get m equals 3 over 2. And that's the case where there's not a unique solution. And we're talking here about any other value for m. So that's not really helping, right? So instead what we're going to do, and we'll talk more about this technique in a later video, we're going to subtract the mx over, and then we're going to factor the x out. So now this is all equal to 0. If it's all equal to 0, either this part's 0, but that part's not 0 because we've decided that m is not equal to 3 over 2. So that means that x has to be 0. And if x is 0, substituting back into, again, either of these, if x is 0, then y is equal to -6. So the solution is going to be 0, -6. And we can verify that with technology. So here's my two lines. I've made a slider for m. And the two lines always intersect at 0, -6. They're going to overlap exactly when m is equal to 3 over 2. So this type of question gets a lot more interesting once we get into 3 equations with 3 unknowns, but I do like this problem for right now because it's got a lot going on, it's got multiple parts, it's got my favorite command term, hence, it's got reasoning, right? So some IB questions are going to require you to communicate in written English, either what your process is or what your result means. So it's an important thing to start getting used to early on. Anyway, that's all of chapter 1. I know this wasn't the shortest video, but we did do one chapter all in one go. So onward to chapter 2, and then eventually we'll slow down once we get into I don't know, some more challenging and interesting mathematics.
When you feel how depressingly slowly you climb, it's well to remember that things take time. And I like this quote for 2 reasons for our course. First of all, there's going to be some people watching this video who are going to be like, come on, man, lines, when are we going to get to the good stuff? Why are we progressing so slowly? And to you, I say, just sit back, relax, enjoy this. Remember that the course is going to always be building upon things that came previously in it. And I don't want anybody in like a year and a half to say, oh, hey, we never covered the fact that every line on a perpendicular bisector is equidistant from the 2 original points. How am I supposed to do this all of a sudden really complicated problem in 3 dimensions? Well, that's why I'm just covering everything from the very beginning. All right? And the second reason that I like it is because there are going to be some people who are going to struggle in this course and who are going to feel that they're not making the same progress as they had, and they're not succeeding at the same level as they have in earlier, quite frankly, easier mathematics courses. And to you, I say, don't be too down on yourself about this. You are progressing. Look back, see how much you've learned, see how much you've grown, and just be proud of that and recognize that mastery takes time. Climbing to the top of this mathematical mountain is going to take time. We're not going to get there all in one. We're going to get there together, and we're going to enjoy the view. It's just going to take some time.